So clearly the SSC members are trying to knock us off our game here, these extra questions. So the man standing between you and lunch is Malcolm Scully, and he is going to continue on with coastal oxygenation. Go for it.
Great, thank you very much. So my name is Malcolm Scully, and I am a physical oceanographer. I work here at WHOI. And I'm going to be talking about the role that physics play in both oxygen dynamics as well as carbon dynamics in estuaries. And I'm going to be doing that using some simplified numerical models. So I'll apologize for two things. First of all, I'm not a biogeochemist, so I'm probably going to simplify something that you care about and study a lot to a simple time invariant coefficient. And I'm also going to talk about carbon, and I realize I was probably supposed to talk only about oxygen in this talk. So the motivation for what I'm going to present is that, as Samantha just highlighted, in the coastal ocean, low oxygen or hypoxia is an issue of ecological importance, but it's also a big issue of economic importance. For instance, in Chesapeake Bay, where I've done a lot of work, it's been estimated that billions of dollars are spent to reduce nutrients, with the main goal being to reduce the occurrence of low oxygen. Estuaries are also thought to be globally important sources of CO2, but I would argue that there's pretty big uncertainties remain about those estimates, and I think we need higher resolution estimates to really constrain those. And so the goal of this talk sort of has two parts. In the first part, I'm going to present some very simplified simulations of oxygen dynamics in Chesapeake Bay, and in the second part, I'm going to show some simulations of a coupled oxygen DIC model of an idealized estuary. And the fundamental conclusion is that the physics is important. I don't know. Mike Roman was correcting my grammar before I got up here. Maybe the physics are important. So part one, I'm going to be looking at oxygen dynamics in Chesapeake Bay, and to do that, I'm going to be using a model called ChesROMS. This was developed by Raleigh Hood and collaborators at the University of Maryland. This is the grid on the right here. It has realistic physical forcing, so it has tides, it has atmospheric forcing such as heat flux, winds, evaporation, precipitation. It's got observed river discharge for the main tributaries. It forces the boundary with observed or estimated salinity and temperature. And what I've added is a very, very simple oxygen model. So the oxygen model that I've added, this is a ROM simulation. It treats oxygen as another tracer, so it's advected and mixed via the advection and diffusion in the model. And all I've done is add a constant consumption of oxygen everywhere in the model domain. This doesn't vary in time and space, but it only removes oxygen from the water inside the estuary. There's no oxygen production, so there's no primary production. And then I set the surface concentration and the open boundary conditions to their saturation value. And then I let the physics do the rest. And so what I'm showing in these four panels is a comparison between the Chesapeake Bay program data of bottom oxygen in these blue circles, and the red is the model prediction of bottom oxygen at these four locations spanning the sort of salinity gradient in Chesapeake Bay. And so the first thing you'll notice is that the model predicts a very strong seasonal cycle with zero oxygen in the summers, much better oxygenated conditions during the winter, and it even gets some of this sort of high frequency variability correct. So this model has absolutely no biological variability, and this just sort of highlights the fact that the physics plays a really important role in this sort of seasonal cycle of hypoxia in Chesapeake Bay. So just to highlight what's driving that, I did some very simplified experiments. So this is a simulation of 2004, and what I'm showing on the y-axis is the Chesapeake Bay program estimate of the volume of water that has an oxygen concentration less than 1 milligram per liter. And so the base run with all the real physics is in gray. And in the top panel, I'm looking at what would happen if you just left the river discharge constant. You didn't let the river discharge vary seasonably. And you see this black line is that prediction, and you see that they're very similar. So that's suggesting that the seasonal variability in freshwater input to the system isn't, at least according to this model, playing a big role in the seasonal cycle of oxygen. The next thing I did is I set the water temperature, the saturation of oxygen equal to water that had a temperature of 25 degrees in the thin black line or 5 degrees in the thick black line. And that's just how much oxygen the water can hold at 100% saturation. And so the thin black line shows that there's much more prevalent hypoxia. And if the water was cold and could only hold a little bit of oxygen, could hold a lot more oxygen, we'd essentially not have hypoxia. So the seasonal cycle of temperature is playing a big role in this seasonal cycle of oxygen. And so if your model gets the temperature right, you're getting close to getting some sort of predictive skill at predicting hypoxia. And the last thing I did is I just played with the winds. I did a simulation where I assumed that the month of July repeated itself 12 times in a row in terms of its wind forcing, and I did the same thing with January. And if the winds blew like they did in July year-round, we'd have hypoxia year-round, according to this model. And if the winds blew like they did in January year-round, we'd essentially have no hypoxia in the system. And so from these simulations, I'd argue there's two fundamental physical controls on this seasonal cycle. One is there's the water temperature, which in the mid-Atlantic region varies quite considerably through the year, and then the wind forcing as well. And so a model with no biology can get a reasonable representation of that seasonal cycle. And so it sort of makes you question how good is a biogeochemical model if we're validating it against oxygen when a model that has no biogeochemistry can actually show predictive skill. So how about interannual variability? So the next thing I did is I took this very simple model and I ran a simulation for 30 years, beginning in 1984, continuing all the way through 2014. And again, this is hypoxic volume in the bay estimated from the Chesapeake Bay program data. The red is the model, and the black are the Chesapeake Bay program estimates from individual cruises. And so every circle matches another circle, so the model is analyzed similar to the way that the data was collected. And again, what's really apparent is the seasonal cycle, but there is interannual variability between these years. And to sort of highlight that a little more, here's some more statistics, but this is just taking every single cruise on the y-axis, comparing it to the model prediction for 3 different definitions of hypoxia, and the skill is high for the 2 milligram per liter cutoff. It decreases for the sort of anoxic condition, but that's really, those statistics are really driven by the seasonal variability. So then I took all 30 years of data and I just averaged it as a function of month, and this is just the correlation coefficient on the y-axis. And so as we go into the summer months, we see high correlation coefficients, particularly for this 2 milligram per liter criteria. And so particularly for July and August, a model that has no biological variability can capture about 50% of the observed interannual variability. And according to the model, that variability is being driven primarily by variations in wind forcing. So I'm going to run out of time, I'm sure, but I do want to show some data because we've had a lot of talks about models today, and I like models, but I also like data as well. I had an observational program in Chesapeake Bay, so the Susquehanna River comes in up to the north. That's the dominant source of fresh water. Salt water is down to the south, and I had instruments along the main axis of the bay at these starred regions. And I also did a bunch of surveys. And so in this mid-bay region, I did surveys of oxygen looking after an up-bay wind. So you're looking into the bay. This is to the west, and to the right is the east. And after the wind's blowing up the bay, the interface of oxygen slopes down to the right or to the east. That's because of the rotation of the Earth and Ekman transport, and all this low oxygen water is upwelling and mixing on the shoal to the west. 2 days later, the wind switched around and blew down the bay. Now it's coming out of the page. The Ekman transport's to the right, and the interface is now tilting up to the east. And so these sloshing back and forth are one way in which oxygen gets mixed into the bottom water. The other way is at bathymetric constrictions. And so this region down here in the southern bay is called Rappahannock Shoal. We did a transect across that shoal, moving from up bay to down bay, and you can see the oxygen is being converging and being advected into that lower layer. So in a tidally average sense, the surface flow is going out, the bottom flow is coming in, and I think this is an important region for how oxygen gets ventilated in the upper bay. So these are bottom measurements spanning the northern bay to the southern bay. So this was put out in sort of the late spring all the way through the fall. This is the northern bay, this is the southern bay, and all locations went devoid of oxygen in the summer months. But you see there's a lot more oxygen, particularly in the late summer and early fall to the south. And there's a phasing between the arrival of oxygen at the south, and it sort of propagates as it moves north. And so all of these sort of ventilation events begin in the south, and then they advect to the north. And so I believe that the role of wind is to have isolated mixing, and then we have advective ventilation moving up the bay. Okay, so part 2 is going to look at how physics can impact both oxygen and DIC in sort of a simplified coupled model. So this is a figure from Raymond et al. Showing salinity on the y or on the x-axis and DIC on the x-axis, and these are 12 cruises. And the key point is that there's a very strong along estuary gradient in DIC. And we plot this as a conservative mixing line, and we look for deviations from that to identify sources or sinks of carbon along the system. And so it's going to be highly related to salinity, as is the alkalinity. So this is from Wong, this is data from Chesapeake Bay as well, plotting alkalinity as a function of salinity on the x-axis. So we have this sort of linear relationship between the two, and so I want to try to apply a very simple model to look at how estuarine physics impacts the fate of oxygen and carbon as well. So I have a very idealized model domain. This is my model domain up here. For a more realistic application of this model, Jenny Thomas has a poster looking at the application of this model to Chesapeake Bay. But essentially, I assume that there's an ocean with high salinity, high alkalinity, high DIC water, and the PCO2 is in equilibrium with my idealized atmosphere at 370. And then at the riverine end, I put in zero salinity water, slightly low oxygen water, lower alkalinity, and low DIC. But the PCO2 is elevated, consistent with lots of observations of freshwater ends of estuaries. So I've got primary production that's very idealized. There's no nutrients, there's no phytoplankton, there's no grazing. I'm just prescribing a PI curve. So the production varies in the vertical, but not in the horizontal. I have community respiration that's constant in time and space, consistent with the Chesapeake Bay model. And then I just prescribe the net ecosystem metabolism so that the community respiration in an integrated sense gives you some ecosystem metabolism. Then I basically let the physics do the rest, and I allow oxygen to be exchanged from the surface, and then I just systematically vary the tides, the river discharge, the wind, and some other forcing. So this is just an example from the simulation. We have the ocean to the left, the river to the right. In steady state, the model predicts this along estuary salinity gradient with some vertical stratification. Because of the weak tidal mixing in this example of 0.3, the tidal amplitude is 0.3 meters, we develop low oxygen in the central part of the domain, and we develop high PCO2, which is actually offset up estuary from that, and it's outcropping here in the upper part of the estuary. So we're getting this buildup of DIC due to the respiration exceeding production in the bottom waters. So from a budget point of view, 44 moles of oxygen are coming in, 154 moles per second are being used, and 78 moles are being exported to the ocean, but it's really being done via a two-layer residual estuarine circulation. So 300 moles per second are leaving in the outflowing residual, and 223 moles are coming in that bottom flowing water in a tidally average sense, and then 188 moles per second are fluxing into the system to satisfy the respiratory need of oxygen. If you look at the DIC balance, 84 moles are coming in at the riverine end, 154 moles are being produced of excess DIC, and 73 moles per second are being exported at the ocean. But again, this is being driven by a two-layer estuarine circulation, where we have 2,000 moles per second leaving in the surface layer and nearly 2,000 moles per second coming in at the bottom in a tidally average sense. And so this is 20 times the DIC input that the river is putting in. And so what I hypothesize is that this DIC that's coming in, the particles that I'm not simulating are decomposing, and they're using up oxygen, and they're producing carbon that is then, or producing PCO2 that is upwelling in the upper estuary. And so the outgassing here is 168 moles per second, and that's in excess of the internally produced DIC, and that's being supplied by this input of DIC from both the ocean as well as from the river. But I would argue that this is being converted to PCO2 in these low oxygen bottom waters. So this is just showing it in plan view. This is the looking down on the estuary from above. The ocean is over here. There's stratification. The stratification breaks down as you move up estuary, and that's where all the PCO2 is outgassing. So it's being low oxygen water, respiration exceeds production in the bottom waters, and it is vected up estuary, and it's outgassed in the upper estuary. So even though the net ecosystem metabolism along the system is roughly constant, all of the outgassing of CO2 is occurring in the upper estuary, and it's actually opposite sign right near the mouth. And the reasons for that I don't have time to get into right now. So I want to look at the combined effect of rivers and tides on a system that's in steady state. And so what I'm showing here is the fraction of the CO2 flux that or the fraction of the net ecosystem metabolism that is outgassing as CO2. And so on the x-axis is the tidal amplitude, and on the y-axis is the river discharge. And so I did 77 model runs where I varied different combinations of these parameters. And so in this lower corner, you see that roughly 100% of that internally produced carbon is outgassing. And as you increase the tidal amplitude and you increase the river discharge, less and less of that gets outgassed and more of that gets exported advectively to the coastal ocean. So the net ecosystem metabolism is constant for all of these runs. But what's happening to that internally produced carbon is different. And if you look at what's happening with oxygen, it's a net heterotrophic system, so it's ingassing oxygen. It's ingassing more than is needed for low tidal mixing and low river discharge, and it begins to outgas less, or ingas less, as the tidal mixing go up and the river discharge go down. But the ratio of the CO2 flux to the oxygen flux isn't constant. You see that at low tidal mixing, it's outgas, and it's always less than 1. So the CO2 flux is outgassing always at a lower rate than oxygen is influxing, and that has to do with the prescribed carbonate chemistry of the system. Essentially, mixing turns PCO2 into bicarbonate, and so it really favors advective export as you crank up the mixing. Same thing happens with wind. This is the percent, these are simulations of looking at wind speed, and again, this is the percentage of the gas flux over the net ecosystem metabolism. So for low mixing, it's exporting more carbon than it's producing, and it's ingassing more oxygen than it needs. And as you crank up the mixing, these ratios go down below 1, but the oxygen doesn't go down as much as the carbon does. And so again, highlighting that the mixing is really changing the way the system is processing oxygen and carbon. The last thing I want to show is just the effect of changing the biological rates. So you can increase the primary production and you can increase the respiration in a way that the net ecosystem metabolism doesn't change. And so on the left is a situation with low primary production and respiration, and this is the oxygen field. So you do get an oxygen minimum, but it's not very low. And you don't build up a lot of bottom CO2 in this case, because there just aren't the high rates of respiration in the bottom water to do that. When you crank up the rates but maintain the same net ecosystem metabolism, you begin to generate this low oxygen region, you build up all this PCO2 that gets transported up estuary and gets outgassed. And so as you increase the biological rates, even though the total integrated carbon and oxygen budgets haven't changed, you begin to outgas more and more CO2 and ingas more and more oxygen in excess of the net ecosystem metabolism. So in order to sort of save some time for questions, I'll try to conclude there. I covered a lot, probably too fast, but hopefully I demonstrated that a model with no biological variability can reasonably simulate oxygen at a variety of time scales. The physical variable that contributes most of this variability is the wind. It's not through direct mixing, but through localized mixing and advection that the oxygen gets up the bay. And then in terms of DIC and oxygen coupled dynamics, the intensity of the vertical mixing really plays a key role in how the system is processing both DIC and oxygen. Oxygen, they both are advectively exchanged as you increase tidal mixing and river discharge, but the CO2 responds more strongly because of the underlying carbonate chemistry. I didn't show this. I removed it before the talk for time, but the piston velocity simulations are very insensitive to how you parameterize the gas exchange coefficient. And then finally, these systems that are very productive or eutrophic with high rates are going to tend to outgas CO2 more and ingas oxygen more, and lower biological rates are going to favor advective exchange. Thank you very much.
Hi, Chris Sabine from Hawaii. Since you took it out, I'd like to comment on your fourth conclusion and ask, we know that the equilibration time for CO2 is significantly longer than oxygen, so I'm curious how the piston velocity cannot be an issue when you talk about those substantial fluxes across the air-sea interface.
So I think here's the result that I didn't show, but This is looking at the surface flux with the Wynecroft formulation, the Raymond formulation, and the Zappel formulation, and this is the integrated flux. And so there are sort of localized differences, but in general, the system is going to get rid of the CO2 and pull in the oxygen however it needs to. It's got to sort of satisfy the long channel convergences in transport. And so there might be slight differences at one location, but if you don't outgas it at one location because the piston velocity is a little lower, it's just going to be more available to outgas slightly downriver. And so there are differences at any given location, but in an integrated sense, the fluxes are very, very similar.
Is this oxygen or carbon?
This is carbon, but it's very similar for oxygen. And then the point is, if I take the Wynecroft formulation, where I prescribe the piston velocity, but I don't actually let the winds do any mixing, you get a very different story in this corner. And so the effect of the mixing and its control on what water is being mixed to the surface is much bigger than any of the changes between the various piston velocities, even though these two formulations are very, very different at high winds, like almost an order of magnitude different.
Hi, I'm Mariana Claret from the University of Washington, GISEO. I saw on your oxygen budget that the circulation of the open oceans affects the region through the bottom waters. So I have, could like a retreat of the Labrador Current and increased presence of Gulf Stream waters could have a slight effect on your oxygen budget here.
Yeah, and so in Chesapeake Bay and some of the East Coast estuaries, I think of the inflowing residual estuarine waters as bringing oxygen in, but there's lots of systems on the West Coast where upwelling can actually bring low oxygen water to the mouth of the estuary, and the source of low oxygen in the estuary is advection of low oxygen in. And so the boundary condition for the estuary is very sensitive to what's going on at the coast, absolutely. And so the West Coast systems, they can advect low oxygen water in, and that's the source. It's not always ventilative, it can be a source of hypoxia.
So the lack of the role of biology in setting variability, at least by your conclusions, is surprising. But do you think that you have, say you decrease nutrient loading to these rivers and decreased respiration by a step function, would that, I mean, that should have an influence, right? Not, if not on the variability, at least on the whole of the oxygen budget.
Yeah, so two things. One is that the Chesapeake Bay results are very sensitive to what that rate of respiration is, and that's totally set by the integrated production, and so that's very sensitive to nutrient loading. The second point is when I start adding realistic oxygen production, I can no longer have constant respiration and get good simulations. And so I'm not suggesting that my biology is realistic in any way, shape, or form. I'm trying to just isolate the physics. And the more complicated the biology gets and the more realistic it gets, you have to continue to add more realism to the way you're prescribing these rates. And so when I let the gross primary production vary the way observations tell us it does, the only way to get a seasonal drawdown of oxygen is to allow the respiration to go up commensurately with that increased production to offset that production of oxygen. So they're very linked. And the underlying rates are completely driven by biology, and I'm just setting them arbitrarily. One more over here.
Hi, Malcolm. This is Jeremy Testa from Chesapeake Biological Laboratory. I feel like I've asked you this question before, so forgive me if I have, and I'll try to articulate this question as good as I can. But, you know, my sense about the simulation when, you know, you're setting the biochemical uptake constant is that you're sort of fixing the vertical gradients and the horizontal gradients of oxygen, which I just have this intuition that those gradients are part of what drives the physical replenishment or the lack thereof. And so, you know, have you ever looked at these simulations with these different oxygen uptake rates and tried to diagnose this question of whether the different gradients change the actual sort of mixing rates vertically or the horizontal rates?
Yeah, I have. And so in order to, I've applied the model to Chesapeake Bay, and in order to best match the observational data that I have to prescribe rates that vary along the system. and that has a big effect on the role of advection, say. And so the spatial variability does matter quite a bit in how the system ventilates. And so it also has a big impact on the gas fluxes. Because the depth integrated volume transport is non-divergent, then all of that divergence in the advective fluxes, it's driving when you converge oxygen in a location, you have to outgas it. That's very, very sensitive to how you prescribe the long channel distribution of your rates. And so your point is a good one, and it's certainly, there is a feedback between where the spatial variability in the rates and the physical response to how it gets redistributed.
Anyone else? Okay, I think the AOU is high, so we should break for lunch. Thanks, Malcolm. And join me in thanking the speakers again.